Hello students, we'll be reviewing consolidation exercise 1 for carboxylic acid and derivatives. Okay, so we'll look at question 1. For question 1, you have a nitrogen-based compound. Okay, so you're given the molecular formula to be C9H11ON. Perhaps we can do a quick calculation for the degree of unsaturation. So we know that the maximum number of hydrogen a C9 carbon can have will be 2n plus 2. So in this case, your n is 9. So max number of hydrogen will be 20. But because there's a nitrogen, so we need to account for it by adding one more hydrogen. Yeah. So in this case, the maximum number of hydrogen a 9 carbon unit with 1 nitrogen can have will be 21. So in this case, degree of unsaturation will be 21 minus 11 divided by 2. So we're going to get 5. Okay, so 5 degree unsaturation, likely to have a phenol ring, given the limited amount of information. Okay, for A1, you were told that orange PPT is observed when P is treated with 2,4-dinitrophenolhydrazine. Name the type of reaction that has taken place. Of course, you know that this is a test of aldehydes and or ketones, so the type of reaction will be condensation. Okay, because water molecules will be given off as the byproduct. From this observation, deduce the functional group that could be present in compound P. So I think we have discussed it should be ketone or aldehydes. Okay, so we can write ketones or aldehydes. Okay, if you wish to write carbonyl compounds or carbonyl functional group, I think that is fine, at least at the H2 level. But you know that carbonyl, in fact, is actually just a group that is present in the whole ecosystem. So that is C11O. Yeah, but for the purpose of H2, it's okay to call them carbonyl compounds or carbonyl as a functional group. Yeah, but it might be better to be a little bit more specific here. Ketones and aldehydes. Right, A2, you were told that no silver mirror is formed when P is heated with hot ammonium silver nitrate. You know that this is a test for aldehydes. Okay, right. So they mentioned no silver mirror, so very specific here. So in fact, this is actually Tollens reagent. So from here, you can conclude that we are actually only looking at ketones. So aldehyde is not present. So yeah, so this allows us to confirm that one of the function groups present in P is ketones. So I'm going to write ketone out. Okay, then when compound P is reacted with bromine water in excess, white PPT with this particular molecular formula is shown or is produced. So you notice the key thing is 0.7. Okay, so if you are looking at bromine's MR is 79.9. For you to get 0.7 for your MR, that means that 3 bromine must have been added, either substituted or simply added. So I think we can analyze from here. Okay, so given the molecular formula, okay, C9H11ON, so C9 will be we need to take 12 multiplied by 9. Okay, so that will give us 108. Okay, with 11 hydrogen, so that will be 119 with 1 oxygen and 1 nitrogen. Okay, so that will be 30, so 149. Okay, and the new MR is 385.7. So you know that 3Br has been added. So if we add 3Br in, so that will be 9.9 times 3, 80 times 3, 240. 240, that will be 239.7. Okay, so from here you will get 8.7, 1858, 388.7. Do take note the difference in the MR calculated. Yeah, so from here we can tell that it is a substitution reaction because 3 hydrogen has been substituted with 3 bromines. So 3H sub by 3Br. So in this case, it is definitely going to be electrophilic substitution. Yep, and my apologies over here because in the enthusiasm of finding a question, I have unknowingly include one little concept from the next topic, which is topic 19. Okay, most of you might be thinking it is a phenol because that's the only thing you have learned. Yeah, but you notice that one of the only oxygen is being taken up by the ketones. Yeah, so this unknown cannot be a phenol. So it is actually phenolamine or aminobenzene. So this allows us to sort of be able to tell us that my unknown contains NH2 directly bonded to the phenol ring. NH2 work similarly to a OH, so it will enhance the reactivity of the benzene ring towards electrophilic substitution. Okay, so from here the molecular formula we can deduce it easily, so that will be C9, okay, minus 3 H's, so it will be C9H8 ONBr3. Okay, so that will be the answer for part 3. Compound P reacts with hot KMnO4 in aqueous sodium hydroxide. So to give this particular molecular formula, the product with this particular molecular formula, you notice there are two sodium here. So the sodium is likely to be the counter cation. So you are asked to draw the structure of the unknowns. Only left with 8 carbons. So therefore likely to be some form of oxidative cleavage. Okay, so we are familiar with the fact that there must be a minor group, so it's phenolamine, so NH2. And in order for 3Br to be substituted into the phenol ring, I must keep the second position, the fourth position, and the sixth position empty. Yeah, so therefore the remaining position must be filled with the remaining substituents. Yeah, in this case the substituent of the products. Okay, so if we look at this particular information, okay, so what's going to happen is that I'm just going to subtract this NH2 away from what I'm given here. So I have C8H5 KH5 NO4 Na2, right? Okay, so I'm going to subtract NH2, so NH2, okay, 6 carbon from the benzene ring, C6, okay, and then of course these 3 position will be the H3, okay, because they contain H. Okay, after I subtract them off, you realize that you're left with 2 carbon, 0 hydrogen, 0 nitrogen, 4 oxygen, and 2 sodium. Yeah, so therefore over here now I can conclude that this is likely to be the carboxylate salt. So COO minus Na plus, and then COO minus Na plus. Okay, so this will be the answer I'm going to give for part 4. Okay, then for part 5, you now have enough information to determine the structure formula of P, draw the structure of P, explain how you have placed each of the 2 functional groups. Okay, so based on this, I'm going to show what my P is likely to be. So my P is likely to, again, phenolamine. Okay, and of course, I'm going to keep 2, 4, 6 empty. Okay, so one of it is likely due to a ketone. Okay, because upon side chain oxidation, one of the carbon is gone. Okay, so therefore one of the side chain must contain 2 carbon. Then the other side chain is just likely to be a CH3. Okay, yeah, so the CH3 undergoes side chain oxidation to give me the carboxylate salts. The ketone N undergoes side chain oxidation to give me the other carboxylate salts. Yeah, so the structure formula of my unknown P is likely to be the one I have drawn in blue. Okay, so it's a pretty straightforward question, but as I mentioned, you will need the concept of topic 19, that is electrophilic substitution of phenolamine using bromine water at room temperature to help you. So it is this particular concept, NH2, okay, phenol ring, and then I'll just have bromine water. Okay, and then I'm going to end up with the 2,4,6 tri-bromophenolamin. Okay, Br. It works similarly as phenol, so 3HBr aqueous. Okay, right. So it should be pretty straightforward, except that you probably have not learned this particular reaction if you have not looked into nitrogen compounds. Okay, then next we'll do part B. So we have a constitutional isomer of P, which is Q. The diagram below shows possible reaction scheme of converting Q to T. So T is unknown. So we have a Q here. Again, a phenyl ring with a primary amine and a ketone. And then it's converted to R. And then you notice that a new function group is being formed. That is an amide. Okay, so how do we form an amide? So in order to form an amide, my R is likely to be some acyl chloride together with NH2. Okay, so I will need to produce an acyl chloride so that the amino group can undergo electrophilic substitution. Okay, I think I've drawn one less carbon. Okay, so I'm just going to draw the NH2 here. Okay, so it's going to undergo electrophilic substitution. Yeah, then how do I convert my Q to R? So that will be a challenging one, I guess, at least at this stage, because you're supposed to suggest reagents and conditions for step 1. Okay, so what I'm going to do is I'm going to perform an iodoform test. Okay, so first I will perform an iodoform test and then acidify the solution in order to produce the carboxylic acid. Okay, so likely that my over here my R is likely to be a carboxylic acid, okay, with NH2. Yeah, but you might be aware that upon performing the iodoform test, because it's in an acidic environment, okay, so the amino group is likely to be protonated. Yeah, but because this is somewhat an open-ended kind of question that they didn't give you much detail as to, because you are supposed to decide on the reagents and condition, right? So it becomes a little bit difficult for you to sort of decide whether it is entirely necessary for me to actually convert the NH2 in to convert the protonated form of amino group back to the NH2 form. Yeah, so this might be, I mean, it's open-ended in the sense that if you wish to, you could do that, right? If not, then my step 1 will simply be the iodoform test condition. So I'll just write out the answer first. I2NaOH warm, and then this is followed by acidification using HCl. So if I do that, then in this case, I'm going to get the protonated form like this. Okay, however, in step 2, right, some form of buffering is required, because eventually I will need to convert my carboxylic acid into an acyl chloride. Yeah, and then after it's converted to acyl chloride, I will need to ensure that the intramolecular nucleophilic substitution or intramolecular condensation can take place. Yeah, so in this case, my step 2, I would likely to just input thionyl chloride. Okay, yeah, but I have to admit that this particular questions, which I've taken from, I forgot the source, is not the most ideal question, because it requires the students to think through some of this complex situation, which at this stage it might be a bit confusing. Yeah, so do not be worried. I think in the future, whenever we give the students question to do in exam, we'll try to be as explicit as possible, or as less ambiguous as possible. Yeah, but for the nature of this question, the testing point, it is really we are just trying to see if the students are able to perform condensation reaction or to form a cyclic amide in this kind of reaction scheme. Okay, yeah, so I think we don't have to be too upset over the situation when what question should we be looking at, and how can we convert R to S, or what exactly is the structure for R, so it's not so important. Okay, so in that case, my most plausible structure for R will look something like this, and of course I'm just going to erase this, because I don't want you to think that R looks something like what I've drawn below. Okay, then for part 2, step 3 comprised of 2 steps: acid-base reaction to react NaH to with NaH to generate intermediate I. Yeah, so basically this is pretty tough, because if you look at S, right, there isn't any much protonic hydrogen that you can think of within your curriculum, except probably for the one that is directly bonded to nitrogen, because it is the most polar NH, or rather the hydrogen X bond is the most polar amongst all the bonds, because the remaining bonds you have is they are all CHs, and these are not activated CHs. Yeah, so because of that, the nucleophilic substitution, or rather before the nucleophilic substitution take place, right, the acid-base reaction between NaH and S is likely to generate the intermediate that looks something like this. Okay, so I'm just going to draw the intermediates. So intermediate I will look something like this. Oops, sorry. Okay, like this, and okay, and then with a negative charge, 2 dots, and then of course Na plus. Okay, so this is intermediate I, and then let's see, and then the structure of T. So we have bromoethane here. So again, this whole chunk I'm going to just highlight in pink. Is going to behave as a nucleophile, so it's going to perform nucleophilic substitution. So therefore my T will be simply I just redraw the nucleophile, okay, with the N here, okay, and then 2 carbons. Yeah, so it undergoes nucleophilic substitution to give T. Okay, the byproduct, of course, we have sodium hydride. So hydride looks like this. If it grabs a protonic hydrogen from the amides, so the reaction will look something like this: delta minus, delta plus. So you'll be an acid-base reaction, right? So this acid-base will generate hydrogen gas. Yeah, because a H plus and a H minus react, of course you get a hydrogen gas. Okay, then for part 3, unlike compound S, compound Q reacts with bromoethane easily. Explain why this is the case. So if you look at the way it's phrased, so they are trying to say that S do not simply react with bromoethane, which means if you put S together with bromoethane, you are not going to expect reactions at all, or probably you need to leave it for a very long time. Yeah, however, Q can react with it easily. Right. Well, I mean, again, this cuts in a little bit into nitrogen compounds, but from what you learned under halogenal alkanes, you should be able to answer the question over here quite easily. Okay, so again, this primary amine contains a lone pair of the nitrogen, so its electron density is being enhanced by the alkyl group. Yeah, so therefore the primary amine will behave as a good nucleophile. So primary amine, okay, behaves as a good nucleophile. So in that case, it does not need to be activated in order to perform nucleophilic substitution. Yeah, but for the case of this cyclic amide, the lone pairs of electrons, it largely has the p orbital character, and it will delocalize across the CO pi system, like what we have learned under carboxylic acid derivatives. Yeah, so because it is delocalized across a CO pi system, it is less available to donate as the nucleophile, or to behave as a nucleophile. So therefore, its ability to undergo nucleophilic substitution is diminished drastically. Then you might be asking, why is it that upon undergoing acid-base reaction, it can behave as a nucleophile? Okay, so this needs a bit of explanation. Okay, so if you take a look at this particular system, you have a carbon here, then you have O. Okay, so this is a CO pi system. Okay, and then you have the N here. Okay, so I'm not going to draw in. I'm not going to draw in the rest. Okay, so what we are familiar with is this lone pair delocalized across a CO pi system. Okay, and then there is, however, right, a hydrogen being projected towards you in the way I'm drawing it. So essentially, I'm looking at this NH bond. If you deprotonate the hydrogen, right, what you're going to notice is that, I'm just going to erase it. What you're going to notice is that the lone pairs of electrons over here, right, okay, it has a very prominent sp3 character, and it cannot be stabilized. It is not delocalized into any pi system. Yeah, so because of that, this lone pairs of electrons is highly available for nucleophilic substitution, or highly available to be donated to an electron deficient site to effect nucleophilic substitution. Yeah, so that is the reason why upon deprotonation, the intermediate I undergoes nucleophilic substitution readily. Okay, so that's the end of the review to consolidation exercise 1.